Optimization of yield lines in two-way slabs. This video deals with type 5 slabs. The definition of slab types. Type 1 is a rectangular slab on all four sides simply supported. Type 2 is one side is fixed. Type 3, two opposite sides are fixed. Type 4, two adjacent sides are fixed. Type 5, three sides are fixed, and of course type 6, four sides are fixed. So this video will deal with type 5 slabs. Using yield line theory, we know that the rotation axis of the different pieces of the slab will rotate about their support, and we have four rotation axes. And when two rotation axes cross, then the yield line starts at cross point. And it starts with an angle beta 1. So for each corner, there will be a yield line that will start. So now we have the four yield lines. When two yield lines intersect, they will be connected to each other, forming a fifth yield line. Of course, at the fixed supports, there's also a yield line on the three sides. And now we can look at some geometrical characteristics, which is S1, S4, S3, and S2. This type of slab has some conditions, of course. The two-way slab means that the side B must be between A and 2 times A. S1 and S3, of course, must be smaller than the total length B. And S2 plus S4 must be equal to A. Now we will use the Cotanger's rule of triangles, which means that the height of a triangle is equal to the base of a triangle divided by the summation of the cotangles of the two adjacent angles. But we know that the cotangles of 90 minus beta is equal to the tangles of beta. So for S1, this means that it is equal to A divided by the tangles of beta 1 plus the tangles of beta 4. S2 is of course equal to S1 times the tangles of beta 4. And then S3 is the same reasoning, and S4 it is also equal to S3 times the tangles of beta 2. Now, to have a realistic yield line pattern, we know that this yield line here could be parallel to the two yield lines up above and below. So when taking Sx, it's equal to S1 times beta 1, and we take Sy, which is equal to S3 times beta 2. So we know that those two must be equal. And then we can do the same reasoning for SV and SW, gives you this equation. And this will lead to a relationship between the four angles in the slab. You can choose one. For instance, tangles beta 3 can then be expressed in the tangles of the three other angles. You can also choose another angle, it doesn't matter. But we know that we only have three variables and not four. And this is only to obtain a realistic yield line pattern. Now, looking carefully at this situation, we have a symmetry. And this symmetry means that the angle beta 1 and beta 4, the conditions are exactly the same. They share the same leg vertically, and the leg horizontally is also the same. So this means that beta 1 must be equal to beta 4. The same applies for beta 2 and beta 3 because they have the same length of legs and the same conditions. So beta 2 is beta 3. So that means instead of 3 unknowns, we now only are left with 2 unknowns. The condition that S1 plus S3 must be smaller than B can then be translated by substituting S1 and S3 in the inequality that 1 over y1 plus 1 over y2 must be smaller than 2 alpha. y1 is the tangents of beta 1 and y2 is the tangents of beta 2. Of course, every angle beta must be smaller than 90 degrees. So now what do we have? We have the formula that we have seen on the previous slide. We fill in with the symmetric conditions, and we find S1 is A divided by Y1 plus Y4. So we continue. This is still a general formulation, but on the next slide we will see it together with those conditions, what will happen. We take alpha equal to B over A, y2 is equal to y3 because beta 3 is equal to beta 2, the same for y1 and y4. And then we see that S1 is A over 2 y1, and so on. For S2, it's A over 2, and S3, it's A over 2 y1, and S4, it's A over 2, which seems logic. The work done by the external forces, E, divided by the load in kilonewton per square meter, divided by the unity of displacement, is equal to the summation of the triangles, which is S1 times A, but it's a summation of triangles, so it's multiplied by delta over 3. So this is this term. On the right-hand side, we have the same or the similar expression. And what's left is then the rectangular portion, which means that the total load is then equal to A times B minus S1 minus S3, and that then the mean deflection is delta over 2, so that gives rise to this expression. We can substitute for y1 and y2, and then we see that this is the expression of the work done by the external forces. The work done by the internal forces is then equal to, this is the bending moment B projected to the rotation axis, so that's B times the angle of rotation is delta divided by S4. So we got B over S4. Similar, on this side, we have A divided by S3. On this side, B divided by S2. On the other side, B, A divided by S1. And then what is left is B divided by S4 for this yield line, A divided by S3 for this yield line, and B divided by S2 for this yield line. Substituting the variables, we obtain this equation. Now we know that E must be equal to D. From this equation, we can find M, the bending moment. And bending moment is then a function of alpha, which is B over A, y1 and y2, so beta 1 and beta 2. And this is equal to this formulation here. Of course, we have to check if the yield line is possible. When we are going to optimize in y1 and y2, we must choose a combination which is possible. So we always have to check this inequality of this equality. So we have to maximize the function m in the 3 variables. And this is a function that we see in the previous slide. So we do that by taking the derivative according to our y1, make it equal to 0, and we solve to get y1, which gives which will lead to the maximum value of m of the bending moment. So this is the expression of y1 max. Then we can substitute y1 max in this formula here. And then we have a function which is a function of alpha and y2, where y1 is already maximized. So I call it mm. Then we can take the derivative according to y2 and we solve it for y2, but this will lead to the third grade equation, and to write down the solution will be a very lengthy and uncomfortable equation. So what we do is we solve this manually and then take afterwards with all the results, we will take a regression to it. And that's the result of the approximation of the regression. So M max will then be the general formula of M, but substituted with y1 max and y2 max, knowing that y1 max is a function of y2 max and also a function of alpha. Writing this explicitly in alpha is too lengthy to write down on a couple of slides, so we'll use this method. We see that we have the two conditions to maximize the function m of the function of bending moment. The maximum bending moment with the 30, 45, 60 rule is then the general formula for the bending moment with alpha and y1 and y2. Looking at an example, we see that y1 is the tangent of 60 degrees, which is square root of 3. y2 is the tangent of 45 degrees, which is 1. y3 is the tangent of 45 degrees, it's also 1. And then y4 is the tangent of 60 degrees. So this is the 30, 45, 60% rule. We are going to substitute those variables in the formula, in the general formula of the bending moment, and we obtain this formula. We know already from the previous slide what the formula is of the optimized bending moment, which is in fact the general formula for bending moment with y1 equal to y1 max and y2 equal to y2 max. We can now put the ratio of the two into a graph with on the x-axis the range of alpha between 1 and 2. We see then that the extreme values are 96.5% or 96.5 and 98.6, meaning that the difference with the 30, 45, 60 rule is less than, let's say, 4% for a type 5 slab. Let's take an example of a square slab on 3 sides fixed and with a size of 5 meters and a load of 20 kilonewton per square meter. So alpha is 1. The 30, 45, 60% rule is 11, gives you a bending moment of 11.9. The maximum bending moment curing is 12.1 kilonewton meter per meter. So the ratio is 0.986. The angle beta 1 is 75.2 degrees instead of 60. Beta 2 is 53.1 degrees instead of 45. Then we can look at the other extreme when alpha is 2. It means that this side is 5 meters, this is 10 meters, and Q is 20 kilonewton per square meter. Again, we look at the bending moment with the 30, 45, 60 rule, which means the full green lines as yield lines. We obtain 19.5, and then we calculate the maximum bending moment optimized, which is the dotted line, gives you 19.2 kilonewton meter per meter, which gives you a ratio of 0.965. The angle beta 1 is then almost the same, 59.7 or 60 degrees, and beta 2 is 52.33 instead of 45.33 instead of 45. We can rewrite everything in a way that the maximum bending moment as a function of alpha is equal to Q8 squared divided by a coefficient K max, also a function of alpha. And this coefficient depends only on the geometric characteristics. So by just we can now we cannot do this explicitly because m in function of alpha we do not have it in a closed formulation. So we can just make the graph, which is quite simple. It's just k max alpha equals to q8 squared divided by m alpha. And then you will see that on the y-axis k max and on the x-axis it's the range 1 to 2. And you have this different values of k max. Let's give an example of a rectangular slab loaded with 20 kilonewton per square meter. A is 5, B is 7.5, so alpha is 1.5. Then we go to the curve, alpha is 1.5, and we obtain K max is something more than, a little more than 30, and we just round it up to 30.5. You can use the formulation as it is given here, or you can use the graph, which is much more simpler. Then the maximum bending moment is 20 times a squared divided by 30.5 gives you 16.4 kilonewton meter per meter. The angle beta 2 is 46 degree, something a little bit more than the 45, and beta 1 is 65, also a little bit more than the 60 degrees. Now, just to give you a summary of the slab of this type 5, to find this yield pattern, you need the angle beta 1 and beta 2. And you will see that for all different slabs with alpha ranging from 1 to 2, so B over A is 1 to 2, then we see this is the optimized angle of the yield line for beta 1 for this corner. Notice that the beta 1 for the 30, 45, 60 rule, 60. So beta 1, 0 means the beta 1 for this rule is 60, which is the red dotted lines. And the optimized value is always bigger. Then we can do the same for beta 2. The coefficient for the 30, 45, 60 rule is, of course, because we have the same support here, both left and right. So it's 45 degrees. And here you see that the optimum value can be larger or smaller.